Give me 50 minutes and I will make integral calculus, click, forever. You've seen this symbol, that long, curvy S. And you've definitely heard the intimidating terms, U-Substitution. But here's the thing. These aren't just abstract topics from a textbook. They are the tools for calculating accumulation, for finding a total, from the area under a complex curve to the total distance a rocket has traveled. Let's put this in perspective. You already know differential calculus. That was the science of finding an instantaneous rate of change, a slope. Integral calculus, on the other hand, is the science of summing up continuous change to find a total amount, a sum. And that is what we are here to do, to master integral calculus, from slices to totals. My promise is simple. In the next 50 minutes, you won't just memorize these concepts, you will understand them from the ground up. This table right here, this is our roadmap. This is the toolbox you will master. Look at it. You can see all the core techniques. We have the definite integral for finding the exact area under a curve like x squared. We have the fundamental theorem, which is the incredible link between area and slope. And of course, the power tools, U-Substitution, integration by parts, and even methods for handling infinity. Don't worry about the details now. The point is, by the end of these 50 minutes, you will have the skills to solve every single one of these. Because by the end, you will see that the integral symbol is simply a powerful symbol for summation. It's just a fancy S for sum. Let's begin. Let's start with integral calculus's single most important problem: finding the exact area under a curve. Now, forget any complicated formulas you might have heard about for a moment. We are going to solve this with the most basic tool we have, a rectangle. This entire process is called a Riemann sum, and it proves the integral is just a fancy way of adding things up. Okay, here is the motivating problem, our mission. Find the exact area under the curve f of x equals x squared from x equals 0 to x equals 1. Now, you can see the problem right away. The top of this shape is curved. A simple formula like length times width just won't work here. So, we cheat. We approximate. Let's walk through this. Our problem is finding the exact area under x squared from 0 to 1. Step 1. A crude approximation. Let's just use one rectangle. So, n equals 1. What's its width? Well, we go from 1 to 0, so 1 minus 0 divided by our one rectangle gives us a width of 1. Simple. What's its height? Let's just take the height at the very end of the interval, at x equals 1. So f of 1 is 1 squared, which is 1. So the area is just width times height. 1 times 1, which is 1. A huge overestimate. You can see on the screen how much extra space that rectangle covers. Okay, let's try step 2, a better approximation. Let's use 4 rectangles this time, so n equals 4. The width of each little rectangle, our delta x, is now 0.25. The total area is approximately that width, 0.25, multiplied by the sum of all the rectangle heights. So we're adding up f of 0.25, f of 0.5, f of 0.75, and f of 1.0. That comes out to 0.25 times 0.0625 plus 0.25 plus, and so on. Our final area is 0.25 times 1.875, which equals 0.46875. Much better. We're getting closer. You see the pattern here, right? As we increase n, the number of rectangles, the error gets squeezed out. Just look at this table. For step 3, we're doing the squeeze. When the number of rectangles, n, is 10, the approximated area is 0.385. When n is 100, it's 0.33835. 1,000, 0.33383. 10,000, 0.33338. The sum is undeniably closing in on one specific value. 1/3. And that is the core idea. The exact area is the limit of this sum as the number of rectangles, n, approaches infinity. Okay, so this whole process, the slicing, the summing, and the taking a limit, it has a formal symbol. And here it is, the definite integral. I know, it looks complex, it looks intimidating, but here's the secret. It's just a formal description of what we literally just did. Let's break it down using this table. That long curvy s is the integral sign. It's an elongated s for sum. It's the operation of finding the total area. The a and b on the top and bottom are the limits of integration, the start and the end. For us, we went from a equals 0 to b equals 1. The f of x is the integrand. That's just the function defining the height. Our curve was f of x equals x squared. The dx is called the differential. It just represents that infinitely small width, our delta x. And that whole limit of the sum thing on the right, that's the process we just saw. It's the value our sum approached, 1/3. So, we have our exact answer. The integral from 0 to 1 of x squared dx equals 1/3. The method we just learned, with all those rectangles and limits, that gives us the formal definition of an integral. It builds the intuition that it's all just a sum. But let's be honest, calculating that limit every single time is a nightmare. It's slow, it's tedious, and it's complicated. But what if there was a better way? What if there was a shortcut? Well, there is, and it's called the fundamental theorem of calculus, and it provides a truly spectacular shortcut. This theorem, the FTC, reveals a stunning, deep connection between the two main branches of calculus. On one side, you have differential calculus, all about finding slopes. On the other, you have integral calculus, all about finding areas. The theorem states that these two are simply inverse operations. Think about that for a second. Taking an integral undoes a derivative, and taking a derivative undoes an integral. They are perfect opposites. So how does this help us? Well, it all comes down to one core idea, the antiderivative. For our function f of x equals x squared, the key is one simple question. What function, capital F of x, when I take its derivative, gives me back x squared? Let's try to figure this out by reversing the power rule. We know the derivative rule, right? The derivative with respect to x of x to the n equals n times x to the n minus 1. So let's just work backwards. First step. To get x squared, we must have started with something like x cubed. That makes sense. Second step. Let's check our work. What is the derivative of x cubed? Well, it's 3x squared. Okay, that's close, but we have an unwanted 3 in front. We just want x squared, not 3x squared. So, to cancel it, we must have started with a 1/3 out front. Let's try again with our new guess. Capital F of x equals 1/3 x cubed. Let's take the derivative. The derivative with respect to x of 1/3 x cubed equals 1/3 times 3x squared, which just equals x squared. It works perfectly. This function we found, capital F of x equals 1/3 x cubed, is called the antiderivative of f of x equals x squared. And that is the key that unlocks everything. Now for the formula, the engine of integration. The area under f of x from a to b is just the change in its antiderivative, capital F of x, between those points. This is part 2 of the fundamental theorem of calculus. As you can see in this formula, the integral from a to b of f of x dx equals capital F of b minus capital F of a. This turns a brutal infinite sum problem into simple arithmetic.
Let's see the payoff. Let's solve the exact same previous problem, find the area under f of x equals x squared from 0 to 1. The integral from 0 to 1 of x squared dx. Here we go, 3 steps. Step 1, find the antiderivative. We just did that. The antiderivative of f of x equals x squared is capital F of x equals 1/3 x cubed. Step 2, evaluate at the limits where b is 1 and a is 0. So capital F of 1 equals 1/3 times 1 cubed, which is just 1/3. And capital F of 0 equals 1/3 times 0 cubed, which is just 0. Step 3, subtract. The area is capital F of 1 minus capital F of 0, which is 1/3 minus 0, which equals 1/3. Done. Just like that. The same value our Riemann sum was slowly, painfully crawling towards, we just solved in 3 trivial lines. That is the power of this theorem. But this isn't just abstract math. It has a direct physical meaning. Let's connect this to reality by imagining a car moving. Let's say v of t is the velocity of the car at time t, and let's say s of t is the position, or the distance traveled at time t. From differential calculus, you already know that velocity is the derivative of position. In other words, s prime of t equals v of t. And if we flip that around, it means the position, s of t, is the antiderivative of the velocity. So what does the FTC tell us here? The formula says the integral from a to b of v of t dt equals s of b minus s of a. Let's translate that. The left side is the area under the velocity curve. The right side is the change in position, or the total distance traveled. The FTC proves they are the exact same thing. The integral is a tool for finding total accumulation. The fundamental theorem has given us an incredible gift. It transformed the nightmare of infinite sums into one simple task: find the antiderivative. So, our entire ability to solve integrals now hinges on one skill: reversing the process of differentiation. This section is where we build your core library, your reference tool, your integration cheat sheet. Okay, first, let's talk about the indefinite integral and something called plus c. A definite integral, like the integral from 0 to 1 of x squared dx, has limits. Its answer is a number. An indefinite integral, like the integral of x squared dx, has no limits. Its answer is a function. But there's a subtle trap with indefinite integrals. Here's the trap. It's called the vanishing constant. The derivative of 1/3 x cubed is x squared. Okay, but the derivative of 1/3 x cubed plus 5 is also x squared. And the derivative of 1/3 x cubed minus 100 is still x squared. There isn't just one antiderivative, there's a whole family of them. So how do we solve this? The solution is the constant of integration. To account for this, we add plus c to every indefinite integral. So the integral of x squared dx equals 1/3 x cubed plus c. Now, a great question might pop into your head. Why didn't we use plus c when we solved our area problem? That's an excellent question. For a definite integral, the c just cancels out. Watch this.
you'd have capital F of B plus C minus capital F of A plus C. The C's subtract away, and you're left with just capital F of B minus capital F of A. They vanish. So here's the bottom line. For an indefinite integral with no limits, you need plus C. For a definite integral which has limits, you don't need plus C. Got it? Good.
All right, let's build the antiderivative table, your core toolkit. Each line here is just a derivative rule you already know, but run in reverse. First up, the integral of a constant k. That's just kx plus c. For example, the integral of 7dx is 7x plus c. Simple. Next, x to the n. This is the reverse power rule, the workhorse. The antiderivative is x to the n plus 1 divided by n plus 1 plus c. You're going to use this all the time. Now, what about the one exception to the power rule? X to the negative 1, or 1 over x. Its antiderivative is the natural log of the absolute value of x plus c. Remember that special case. The integral of e to the x? That's the easiest one. It's just e to the x plus c. The integral of a to the x? That's a to the x divided by the natural log of a plus c. The integral of cosine of x? That's sine of x plus c. Straightforward. The integral of sine of x? Be careful. It's negative cosine of x plus c. Watch that sign change. It's a super common mistake. And a few more key ones. The integral of secant squared of x is tangent of x plus c. The integral of 1 over 1 plus x squared is arctan of x plus c. This one comes up more often than you'd think. And the integral of 1 over the square root of 1 minus x squared is arcsine of x plus c. Another key inverse trig pattern to know. Okay, now let's talk about some basic properties. The constant multiple rule. This is great. You can just pull constants out front. The integral of c times f of x dx is just c times the integral of f of x dx. For example, the integral of 5x cubed dx, just pull the 5 out front. You get 5 times the integral of x cubed dx. Using the power rule, that becomes 5 times x to the 4th over 4 plus c, or 5/4 x to the 4th plus c. And the other major property, the sum and difference rule. This is huge. It means you can integrate term by term. The integral of f of x plus or minus g of x is just the integral of f of x plus or minus the integral of g of x. Let's do a quick example. Find the integral of cosine of x minus 4x dx. Step 1, split it. It's the integral of cosine of x dx minus the integral of 4x dx. Step 2, integrate the first term. That's sine of x. Step 3, integrate the second term. That's 4 times x squared over 2, which simplifies to 2x squared. Step 4, combine them. The answer is sine of x minus 2x squared plus c. See? You just tackle it piece by piece. Okay, time to put it all together. A complete example. Let's evaluate the definite integral from 1 to 2 of 3x squared plus 4 over x dx. This one combines the sum rule, the constant multiple rule, the power rule, and the 1 over x rule. Let's do this. First, let's find the indefinite integral, term by term. We can split it into the integral of 3x squared dx plus the integral of 4 over x dx. That's the sum rule. Now, pull out the constants. 3 times the integral of x squared dx plus 4 times the integral of 1 over x dx. That's the constant multiple rule. Now we integrate. Using the power and 1 over x rules, we get 3 times x cubed over 3 plus 4 times the natural log of the absolute value of x. The 3's cancel, so our antiderivative, capital F of x, is x cubed plus 4 times the natural log of the absolute value of x. Next, step 2. Apply the fundamental theorem of calculus, capital F of 2 minus capital F of 1. Let's plug in the upper limit. F of 2 equals 2 cubed plus 4 times the natural log of 2. That's 8 plus 4 natural log of 2. Now the lower limit. F of 1 equals 1 cubed plus 4 times the natural log of 1. The natural log of 1 is 0, so this is just 1. We have our two pieces. Finally, step 3. Calculate the final result. The area is 7 plus 4 natural log of 2. That is the exact, perfect answer. It's approximately 9.772. And that's how you use your new toolkit. The basic rules are powerful, but they all share a fatal weakness. They only work on simple functions. What happens when you face a composite function? For example, the integral of 2x times cosine of x squared, dx. None of our rules work here. We're stuck. This is where you learn the master technique. This isn't just another rule. This is the single most important, most powerful, and most used integration method you will ever learn. It's called U-Substitution, and its entire purpose is to reverse the chain rule. Mastering this algorithm is the key to unlocking 80% of the integrals you will ever face. Let's look at the motivating problem. Look at this integral again. The integral of 2x cosine of x squared dx. It contains a secret signal, a function, x squared, and its derivative, 2x, are hanging out together. This is your green light for U-Substitution. Okay, let's break down the foolproof 5-step algorithm. First, step 1, choose U. You need to identify the inner function. Here, x squared is plugged into the cosine function, so let u equal x squared. Step 2. Find du. You just differentiate u with respect to x. So du over dx equals 2x, which means du equals 2x dx. Simple. Step 3. Substitute. This is where the magic happens. We replace all the x terms with u terms. So, the integral of cosine of x squared times 2x dx becomes the integral of cosine of u du. Look how clean that is. The complex part just vanished. Step 4. Integrate. Now you solve the new, simpler integral. The integral of cosine of u du is just sine of u plus c. We know that one. And finally, step 5. Back substitute. The original problem was in terms of x, so our answer has to be 2. Just replace u with what it was, x squared. Final answer, sine of x squared plus c. And you can always check your work. Differentiate the answer with the chain rule. The derivative of sine of x squared plus c is cosine of x squared times 2x. It's a perfect match. Okay, that was a little too perfect. What do you do when the derivative isn't an exact match? Let's look at example 2, when the derivative isn't a perfect match. Here's our problem. The integral of x cubed times x to the 4th plus 5, all raised to the 6th power, dx. Step 1. Choose u. The inner function is clearly x to the 4th plus 5. Let u equal x to the 4th plus 5. Step 2. Find du. Differentiate. Du equals 4x cubed dx. Step 3. Substitute. Uh-oh. We have a problem. Our integral has x cubed dx, but our du gives us 4x cubed dx. This is where people get stuck, but it's just a little algebra. If du equals 4x cubed dx, then just solve for what you need. Divide both sides by 4. 1/4 du equals x cubed dx. Now we have a perfect piece to swap in, so let's substitute. The integral of x to the 4th plus 5 to the 6th times x cubed dx becomes the integral of u to the sixth times 1/4 du. Step 4. Integrate. Pull the constant out and use the reverse power rule. We have 1/4 times the integral of u to the sixth du. That equals 1/4 times u to the seventh over 7 plus c, which simplifies to u to the seventh over 28 plus c. And now, step 5. Back substitute. Replace u with x to the fourth plus 5. Final answer, 1 over 28 times x to the fourth plus 5, all to the seventh power, plus c. Now, for the pro-level shortcut. U-Substitution with definite integrals. When you have limits of integration, you have two choices. There's the long way, where you solve the indefinite integral, back substitute to x, and then use the original x limits. It works, but it's clunky. Then there's the expert way. Change the limits of integration from x values to u values. This lets you skip back substitution entirely. Let's try a problem, a definite integral. Evaluate the integral from 0 to 1 of e to the 5x plus 1 dx. Step 1. Choose u and find du. Pretty standard. U equals 5x plus 1. Du equals 5 dx, which means dx equals 1/5 du. Now for the key step. Step 2. Change the limits. We convert the old x limits to new u limits. Let's start with the lower limit. When x equals 0, then u equals 5 times 0 plus 1, which equals 1. Now the upper limit. When x equals 1, u equals 5 times 1 plus 1, which is 6. Our new limits are 5, 1, and 6. Step 3. Substitute everything. The integral transforms completely into the world of u. The integral from 0 to 1 of e to the 5x plus 1 dx becomes the integral from 1 to 6 of e to the u times 1/5 du. We will never go back to x. So step 4, integrate with the new u limits. We have 1/5 times the integral from 1 to 6 of e to the u du. This equals 1/5 times e to the u evaluated from 1 to 6, which is 1/5 times the quantity e to the sixth minus e to the first. This is the final exact answer. No back substitution needed. It's faster, cleaner, and way less prone to errors. Okay, so far, U-Substitution has been your number one tool. It's fantastic because it reverses the chain rule. But what happens when you run into an integral that was created by the product rule? Let's look at the motivating problem. Take a look at this integral, the integral of x cosine of x dx. Let's think about why our current tools completely fail here. First, basic patterns. This is a product, not a simple antiderivative. Okay, so what about U-Substitution? Well, if you let u equal x, then du equals dx. That doesn't simplify the cosine of x at all. Alright, what if u equals cosine of x? Then du equals negative sine of x dx. That doesn't remove the x out front. You're stuck. We need a new tool. This tool is integration by parts, and it is designed to reverse the product rule. So where does the formula come from? It comes straight from the product rule for differentiation, which you already know. The derivative with respect to x of u times v equals u times dv dx plus v times du dx. Now you just integrate both sides, rearrange the terms a little bit, and you get the formula. The formula for integration by parts. It is the integral of u dv equals uv minus the integral of v du. The entire strategy is to take a difficult integral, the integral of u dv, and transform it into an expression containing a much simpler integral, the integral of v du. Your success depends entirely on how you choose u and the v. To understand this, we're going to do it the wrong way first. Let's learn by failing. This is the art of the choice. Okay, problem. The integral of x cosine of x dx. Attempt 1, a poor choice. Step 1, split it. Let's try u equals cosine of x and dv equals x dx. Step 2, find du and v. If u is cosine x, then du is negative sine x dx. And if dv is x dx, we integrate that to get v equals 1/2 x squared. Alright, step 3. Assemble the formula. uv minus the integral of v du. The integral of x cosine x dx equals cosine x times 1/2 x squared minus the integral of 1/2 x squared times negative sine x dx. Let's clean that up. That gives us 1/2 x squared cosine of x plus 1/2 times the integral of x squared sine of x dx. Stop. Our new integral is harder than what we started with. This choice made the problem worse. Okay, let's try this again. Problem. Integral of x cosine of x dx. Attempt 2, the strategic choice. Step 1, split. This time, let's let u equal x and dv equal cosine of x dx. Step 2, find du and v. If u equals x, then du equals dx. Simple. If dv equals cosine x dx, we integrate to get v equals sine of x. Okay, step 3. Assemble the formula. uv minus the integral of v du. The integral of x cosine x dx equals x times sine x minus the integral of sine of x dx. Success! Look at our new integral. That's one of our basic patterns. We've made the problem simpler. Now we just solve it. Step 4. Solve the new integral. We know the integral of sine of x dx is negative cosine of x. So our expression becomes x sine of x minus negative cosine of x plus c. Step 5, the final answer. X sine of x plus cosine of x plus c. So how do you make the right choice every single time? Why did u equals x work so well? Because its derivative, du equals dx, was simpler than x itself. This leads to the unforgettable mnemonic for how to choose u. Here's the secret. Pick u to be the first type of function that appears in your integral from this priority list. LIATE. That's L for logarithmic, like natural log of x. I for inverse trig, like arctan of x. A for algebraic, like x squared or 3x. T for trigonometric, like sine of x. And E for exponential, like e to the x. Let's test it on our problem, the integral of x cosine of x dx. We have an algebraic function, x, and a trigonometric function, cosine of x. In Liate, a comes before t, so we correctly choose u equals x. It works. Every time. Now for the natural log of x trick. Let me show you its unexpected power. What about this integral? The integral of natural log of x dx. This doesn't look like a product. Or is it? We can rewrite the integral of natural log of x dx as the integral of natural log of x times 1 dx. Haha. Now we use Liate. We have a logarithmic function, natural log of x, and an algebraic function, the number 1. L is the highest priority. So step 1, we split. U equals natural log of x, and dv equals 1 dx. Step 2, find du and v. The derivative of natural log x is 1 over x, so du is 1 over x dx. The integral of 1 is just x, so v equals x. Step 3, assemble. The integral of natural log of x dx equals natural log of x times x minus the integral of x times 1 over x dx. Step 4, solve and simplify. That becomes x times the natural log of x minus the integral of just 1 dx. And the final answer is x times the natural log of x minus x plus c. This is a classic, powerful result that you can only get using integration by parts. We've mastered reversing the chain rule and the product rule, but a new enemy awaits: rational functions. First question:
How would you solve this? The integral of 1 over x squared minus 4 dx. Let's think. U-Substitution? No obvious inner function. Integration by parts? It's not a product of two different types of functions. We're stuck again. But what if I told you the solution has almost nothing to do with calculus? What if it's just a clever algebra puzzle? That's exactly what partial fraction decomposition is. It's an algebraic method for taking one complicated fraction and ripping it apart into a sum of several simple fractions.
Our mission is to break 1 over x squared minus 4 into simpler pieces. The core idea is that this complicated fraction came from adding two simpler fractions together. Something like a over x minus 2 plus b over x plus 2. So let's do it. Step 1. Factor the denominator. This is essential. X squared minus 4 becomes x minus 2 times x plus 2. Easy enough. Step 2. Set up the decomposition. We write our original fraction, 1 over parentheses x minus 2 times x plus 2, equals a over x minus 2 plus b over x plus 2. Our entire goal is to find the numbers a and b. Step 3. Clear the denominators. This is where we get rid of the fractions. Multiply both sides by that original denominator, x minus 2 times x plus 2. What are we left with? 1 equals a times x plus 2 plus b times x minus 2. This is our key equation. Step 4. Solve for the constants. Now, this equation has to be true for all values of x, and we have two great methods to solve it. Method 1 is the Heaviside cover-up method. It's fast, it's simple, you just choose clever x values to make terms disappear. Method 2 is equating coefficients. It's a bit more general. You expand everything and match the coefficients for each power of x. Let's start with the fast one. Method 1, the Heaviside cover-up. Our key equation is 1 equals a times x plus 2 plus b times x minus 2. To find a, we need to make the b term disappear. How can we do that? We can set its factor x minus 2 to 0. So, let's let x equal 2. We get 1 equals a times 4 plus b times 0. That means 1 equals 4a. So a equals 1/4. We're halfway there. Now, to find b, let's make the a term disappear. We'll set x equal to -2. That gives us 1 equals a times 0 plus b times -4. So 1 equals -4b. b must be -1/4. Puzzle solved. Now for method 2, equating coefficients. It's a little more formal. We start with the same key equation. 1 equals a times x plus 2 plus b times x minus 2. Step 1 is to expand and group by the powers of x. So 1 equals ax plus 2a plus bx minus 2b. Let's group the x terms. That's 1 equals a plus b times x plus 2a minus 2b. Step 2, we match the coefficients. The left side is really just 0x plus 1. So, for the x to the power of 1 terms, a plus b must equal 0. For the constant terms, 2a minus 2b must equal 1. Step 3 is just to solve that system of two equations. And when you do, you get the exact same answer. A equals 1/4 and b equals -1/4. Step 5. Rewrite and solve the integral. This is the payoff. Now we replace our one difficult integral with two simple ones. The integral of 1 over x squared minus 4 dx becomes the integral of 1/4 over x minus 2 plus -1/4 over x plus 2 all dx. Let's pull out those constants. That equals 1/4 times the integral of 1 over x minus 2 dx minus 1/4 times the integral of 1 over x plus 2 dx. And what's the final answer?
both of these are just the natural log rule from our toolkit. The answer is 1/4 natural log of the absolute value of x minus 2 minus 1/4 natural log of the absolute value of x plus 2 plus c. We turned an unsolvable problem into 2 easy logs. But before you get too excited, you need to watch out for these traps. Trap 1, the degree check. Partial fractions only works if the numerator's degree is less than the denominator's degree. So for example, the integral of x plus 1 over x squared minus 4 dx. This works. Numerator degree is 1, denominator is 2. Okay. But this one, the integral of x cubed plus 2x over x squared minus 1 dx, this doesn't work. The numerator degree is 3, denominator is 2. You would need to do polynomial long division first. Trap 2. Repeated factors. When a factor appears multiple times, you need separate terms for each power. So if your problem is the integral of 3x plus 1 over parentheses x minus 2 squared times x plus 1, this setup is wrong. A over x minus 2 squared plus b over x plus 1. You're missing a term. The correct setup is a over x minus 2 plus b over x minus 2 squared plus c over x plus 1. Each power gets its own term. And trap 3, irreducible quadratics. These are quadratic factors that can't be factored any further, and they need linear numerators. Look at this problem. The integral of 5x squared plus 3x plus 1 over x minus 1 times x squared plus 1. Note that x squared plus 1 has no real roots. You can't factor it. So this setup is wrong. A over x minus 1 plus b over x squared plus 1. That constant numerator is the mistake. The correct setup is a over x minus 1 plus bx plus c over x squared plus 1. You need that linear numerator, bx plus c. Keep these rules in mind and you'll be unstoppable. You now have a powerful set of tools. But your journey isn't over. We have to confront 2 final, challenging questions. First, what happens when the area you want to measure is infinitely long? And second, what do you do when a function has no formula for its integral? Let's start by taming infinity. Part 1. Improper integrals. Here's the motivating problem. Find the area under the curve f of x equals 1 over x squared from x equals 1 to x equals infinity. The integral from 1 to infinity of 1 over x squared dx. As you can see, this region goes on forever. Your intuition might scream that the area must be, well, infinite. But let's test that idea. Here's the problem. Infinity isn't a number. You can't just plug it into the fundamental theorem of calculus. So we have to be clever. We're going to sneak up on infinity using a limit. Here's the approach for the integral from 1 to infinity of 1 over x squared dx. Step 1. Replace infinity with a variable. We'll just swap out infinity with a placeholder. We'll call it b, and then let b approach infinity. So we have the limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx. Easy enough. Step 2. Solve the definite integral. So we focus on the integral part. We take the limit as b approaches infinity of, well, the antiderivative of 1 over x squared is negative 1 over x. We evaluate that from 1 to b. Plugging in the limits gives us the limit as b approaches infinity of negative 1 over b minus negative 1 over 1, which simplifies to the limit as b approaches infinity of 1 minus 1 over b. Okay, we're at the final step. Step 3. Evaluate the limit. As b gets unimaginably large, what happens to that tiny fraction, 1 over b? It goes to 0, which means our limit is just 1 minus 0, which equals 1.
The result is stunning. The total area of this infinitely long region is exactly 1. When an improper integral gives a finite number like this, we say that it converges. But does this always work? Let's try another one. This is convergence versus divergence. Let's change the function slightly. Now we'll look at the integral from 1 to infinity of 1 over x dx. Let's follow the same steps. 1. Set up the limit. The limit as b approaches infinity of the integral from 1 to b of 1 over x dx. 2. Solve the integral. That's the limit as b approaches infinity of the natural log of the absolute value of x, evaluated from 1 to b. And 3. Evaluate. This becomes the limit as b approaches infinity of the natural log of b minus the natural log of 1. Since the natural log of 1 is 0, we're left with just the limit as b approaches infinity of the natural log of b. So, what is the limit as b goes to infinity of the natural log of b? The natural log function just keeps growing and growing forever. The limit is infinity. This area is infinite. We say this integral diverges. So here's the tale of two functions. For the integral of 1 over x squared, the function shrinks to 0 fast enough, so the integral converges to 1. For the integral of 1 over x, the function shrinks to 0 too slowly, so the integral diverges to infinity. This leads to a really useful rule of thumb, the p-integral rule. For integrals that look like 1 over x to the p from 1 to infinity, the integral converges if p is greater than 1, and diverges if p is less than or equal to 1. A crucial shortcut. Part 2. When formulas fail. Numerical integration. Okay, we've handled infinity. But what about that second, even scarier question? What if a function just can't be integrated? Consider this monster, the integral from 0 to 1 of e to the negative x squared dx. This is the bell curve, the absolute backbone of statistics, and it has a dark secret. It has no elementary antiderivative. I'm serious. Our entire toolkit, the fundamental theorem of calculus, U-Substitution, integration by parts, is completely useless here. We're stuck. So what do? We go back to the beginning. When we can't find an exact answer, we approximate. This is called numerical integration. It's how computers solve most real-world integrals. Instead of finding a perfect formula, we just add up a bunch of simple shapes. We can do better than rectangles, though. We use trapezoids. They hug the curve much more closely, which means less error. This leads us to the trapezoid rule. The formula looks a little intense, but the idea is simple. To find the area, you take delta x divided by 2 and multiply it by the sum of the function heights. But here's the key. The first and last points are used once, but all the interior points are used twice. Let's try it on our impossible problem, the integral from 0 to 1 of e to the negative x squared dx. And we'll just use 4 trapezoids, so n equals 4. First, we find delta x. That's the total width. 1 minus 0 divided by the number of trapezoids, 4. So delta x is 0.25. Second, we find the function values at each point. F of 0 is e to the 0, which is 1. F of 0.25 is about 0.939. F of 0.5 is about 0.779. F of 0.75 is about 0.570. And finally, f of 1 is e to the negative 1. Okay, got all our pieces. Step 3. Plug everything into the formula. The area is approximately 0.25 divided by 2 times 1 plus 2 times 0.939 plus 2 times 0.779 plus 2 times 0.570 plus our last point. Phew. Let's simplify. Add all that up, 0.7430. So how close did we get? The actual value is about 0.7468. Our approximation is 0.7430. With just 4 simple trapezoids, we're already incredibly close. So what's the takeaway here? When perfect formulas fail, we don't give up. We return to the fundamental idea of integration, summing up simple slices. This is how the real world gets things done.
We've come to the end of our journey. We have systematically deconstructed integral calculus from the intuitive, foundational concept of a Riemann sum to the incredible power of the fundamental theorem and all the master techniques that make it work. Look at this. This is your complete calculus toolbox. We started with the definite integral, the core idea of finding the exact area under a curve, like the integral from 0 to 1 of x squared dx. Then came the big one, the fundamental theorem, the magical link between area and slope, between integrals and derivatives. From there, we built out your toolkit, the basic antiderivative patterns, your reverse power rule, your integral of e to the x, your trig functions. Then we brought out the heavy machinery, U-Substitution, the reverse of the chain rule, and without a doubt, our most powerful tool, integration by parts, for unwinding the product rule. Partial fractions, that brilliant algebraic trick for breaking down those messy rational functions. And finally, we looked at the real world, improper and numerical integration, showing you how to handle infinity and how to get an answer even when no perfect formula exists. That's it. Every concept, every technique, you've seen it, you've practiced it, and now you understand it. Integral calculus now clicks.